We talked very much about the effect on the adult corals, but there's a very, very important stage here, which is the effect of sediments and turbidity on the reproductive cycle of the corals, especially on the juvenile corals. What I've got is I've got some videos in here, so you can, and I'll talk you through it so you can conceptually understand what this is all about. The 1983, it was actually here in Magnetic Island. It was people like Russ Babcock, Peter Harrison, sort of old scientists from 20, 30 years ago, discovered this effect here. This is the coral spawning. So what they discovered was that the corals actually release all their gametes every, say, biannually or annually over 3 or 4 nights usually in the springtime, in a sort of an epidemic spawning event. So what you're seeing on the left-hand side there is a symbolic, and I'll show you a video of this in a second, is a coral spawning eggs and sperm bundle. So up here are egg and sperm bundles which are released from the coral, and these float straight up to the surface. The significance of when they discovered the coral spawning, they did talk about a rain squall event that occurred whilst in the science paper that they produced, and the rain squall event destroyed all the propagules, are the words that they used at the time, and they flagged that as a management issue. And that was actually picked up very, very quickly over in West Australia, where in '93 they started restricting all form of dredging during the coral spawning period. It's probably the most contentious regulation and condition in coral spawning in Western Australia, because it means they actually have to stop all the dredging as this occurs. So the egg sperm bundles, they reach the surface, and then the egg sperm bundle dissociates, and then fertilization occurs. So you can see an egg sperm at the top there at number 3, and then you go through a development stage, and you can see the numbers there are hours, how many hours it takes, 3 hours, 5 hours, 6 hours, as they go through embryogenesis. They start one cell dividing into 2 and 4 and 8 and so on. They're in the water column for sometimes upwards of a week, 10 days, and they gradually turn into something when they start moving, they're called a larvae, and then the term is planulae as well. And they then actually go from this planktonic phase back down to the seabed. So they could have drifted out and never find a reef again, or they could start drifting around Magnetic Island here and actually find a place to settle. And then there's a really crucial stage when they actually settle on the seabed. And they're very, very sensitive at that stage. I'll show some pictures to that effect. Once they settle, they metamorphosize, they start calcifying, they then turn into the primary polyp, and the polyp starts budding, and then with about 1.5 to 2 years later, they can actually complete their cycle, and they're reproductively they're mature. So I just broke my glasses a minute ago, so I can't actually see what's going on here. But you've got a mouse. There we go. So I'm after a video, sorry. So this will be a video of that life cycle run reasonably quickly. I can try and annotate it, but chances are it'll be too fast. So egg sperm bundles rising from the surface. You'll see a fertilization stage at the surface. Those are eggs and sperm there. This is the 2, 4, 6, the early embryogenesis stages. So this is all occurring on the water surface. They descend down into the water column. They turn into a larvae or planulae, and then it's quite rapid. This is where they hit the bottom, and if it's right, if it's an appropriate site, they will settle, metamorphosize, start calcifying, and then form budding, and then go to forming a juvenile coral. So this is, as I said, it's a critical stage for the effects of sediments on corals, and most of what we've been doing, yeah, and it's different down here than it is on the screen. So what we've been doing at AIMS is actually to try and work our way systematically through every single one of those stages, and it's the same sort of principle. We talk about cause-effect pathways and the mechanisms. So we looked at the egg sperm bundle rise, if you could press enter. So what you're seeing there is egg sperm bundles. It turns out that sediments actually bind onto the egg sperm bundles, which is very, very unusual, and it can actually stop the egg sperm bundles from rising to the surface if the concentrations are high enough. You've got to be high. You're literally walking tens of meters away from a dredge in that case, but it is a valid cause-effect pathway. If they don't get it to the surface, they can't break up, fertilization doesn't occur. Go to the second stage, And again, click once, twice, and another one. That's it. So those blue, I don't know if you can make out the blue. The blue are false color. They're the actual sperm. What the sperm do is they get caught up in the sediment. Now, how the sperm are naturally negatively buoyant. The eggs are on the surface. The sperm are trying to get up to the eggs to fertilize them. If they get tangled up with sediment that's also settling out, then it actually strips the sperm from the water column, which is quite a significant effect. Again, depends on your sediment concentration, and a lot of this is to do with timing. Melinda's got it. We're going on to the next stage. So we're going on to the stage when they're in the water column, and they're going all the way through until they turn into the planulae. And that one is remarkably insensitive. You can really hit them with very, very high sediment concentrations, and it really has no effect. The key one is the settlement phase. Can you go back or page down? So the settlement phase, when they start hitting the reef and when they start settling, that's very important. Can I jump in there and do some stuff now? No, there's a tiny little thing you got to click there to. All right, straight away. So we'll play it a couple of times. There's amazing footage here of, they look like maggots feeding off in your wheelie bin off of a steak, but those are the planulae, and they're tiny little things, less than a millimeter across. And what they did there, can we play that one again? So press on that S, the button S. So what I see on the screen is different from here. So press on the S. So they're just buzzing around. They're searching for an area to settle. And when they're happy, and this is crustose coralline algae, when they're happy, they settle usually in clumps. And it's incredible footage. I said to the guy who did this as one of my PhD students, it's 25 years worth of research. People like Jod would know just how much work has gone into figuring out, from not knowing how the reproductive cycle works to actually knowing when to bring them in, when to put them into buckets, and just hold on a second. Put them into buckets, how to mix the egg sperm concentrations to get them to develop, how you develop them for how many periods of time before, and even to try and get them to settle on something. So if you press that where it says SS, so this is what they do with respect to sediment. So the sediment's on the left-hand side. You can see they're really not averse to anything to do with the sediment. They actually love it. They're playing around it. They're actually detecting settlement cues from the coralline algae, and they're trying to find the settlement cues. So they're burrowing through it. Can we rewind again? But if you look, they will not settle anywhere near loose sediment. So that's the little SS. That looks better. So they will settle actually in this area around here. Look at this. They're actually tucked right beside the sediment. So they'll actually settle in that. They're quite happy with the fact that beside them is sort of a couple of millimeters worth of sediment. The area in the middle here, which is a little bit of sprinkling of sediment, just like sort of salt on a steak, that's fine. They will not settle there. So that's in the region of 1 to 10 milligrams per litre, very, very low concentrations. So we've written this stuff up. It's on the website. There's publications to this effect. Those are the publications, and it's all coming out literally. If you look at the dates of these things, they're in the last couple of months that we've been producing all this stuff. But the fact is, there are different. The whole cycle. You've got to look at all the different cause-effect pathways. Looking at the dose response, there are areas that are quite sensitive. Now, this was picked up, as I said, back in 1993. By the West Australian people. It's picked up by Marine Parks Authority. I think they have conditions over it. They call it windows of environmental sensitivity, and it's contentious because you're not allowed to dredge. It's the only time they have in West Australia that you can't dredge. They'll have the same sort of things here. We see the settlement stage of the larvae on the reef as one of the most critical things. They will not settle if there's any sediment anywhere, but what they'll do is they'll find somewhere else to settle. So they'll get a little underhang, they'll find a clean area. There's always got a clean area on a reef. So the question then becomes, they're settling in a suboptimal place. What does that have ecologically on them in the long term? So when we talk about sort of long-term changes in Magnetic Island and the reefs, that might not be manifesting itself at the adult level, the physiology of the adults. It might be more manifesting itself at a community level, at an ecological level over time. And that's over a 10-year thing. You got your hat on, you want your glasses. No, so we have a postdoc who's probably starting in the next couple of months, actually looking at that early life, the settlement stage and the early life history stage. So the post-settlement mortality, which is the couple of months afterwards, is a very, very important stage. It's the missing link for us at the moment.